about global optimization when the target functions has a low rank representation.
Thank you, Mattia. Thank you for the invitation to talk in this workshop. So yeah, I'm going to explain also a bit about the moment SOS hierarchies and specifically how to exploit some type of structure, which we call rank structure polynomials. This is a joint work with Didier Rion and Milan Corda at LAS in Toulouse. And yeah, let's go with it. So first I'm going to present the problem. So we have a polynomial optimization problem. So basically we want to find some p star that minimizes this p of x. We have to find the minimum value and the excess that minimizes this value. Such that these constraints, these polynomial constraints, and g of j are satisfied. So to do this, we want to globally minimize this, so we use the moment SOS hierarchy. So I'll be very brief with this because people introduced it already. But basically what we do is go from the problem in X to a problem in a measure, in a probability measure, this mu. And when we do this, so this probability measure defines some sequence of moments, this y. And this allows us to rewrite the problem, the original problem, into a sequence of semi-definite programs. Okay, so this measure defines these y's, and these y's allow us to write this p star as the infimum over this sequence of moments of this L of y is a linear, so we linearize the polynomial. So now I'll show an example and see how this is done. But basically the idea is that this measure defines these y's, and there's an infinite sequence of these y's. Okay, so to make this problem tractable, which we mentioned before that this problem here is empty hard. Want to make it tractable, we go to these probability measures that define some y's, but infinitely many of them. So what we do to make this tractable is instead of taking the infinite many y's or moments, we take finitely many of them. And depending on how many moments we take, how many y's, this SDP will be larger or smaller. Okay, and it will increase the size with this order. Okay, so the problem we'll have is some relaxation of the original problem, and as we increase the relaxation order, as we increase k, we will have a tighter and tighter problem to the original problem. Okay, so in this relaxation, we will have a linear, instead of a polynomial, we'll have a linear function as the cost function here, the objective function, and then we will have some PSD constraints that will be the bottleneck of our method. So it will be they will drive the complexity. Okay, so the objective of this talk is to basically handle the size of this PSD matrix to make it as small as possible. Okay. Yeah, so just an example. So imagine we have this polynomial here. So we move to the probability measures. So we define these moments. So this, instead of the objective function being a polynomial, now it will be a linear function of these moments, you can see. And this moment matrix, so this we fix the relaxation order to be 2 here for this example. And this moment matrix includes the moments here. And this will be the size of the matrix that we need to check to be positive semi-definite. Okay. And as we increase the relaxation order and the number of variables, the moment matrix increases with this combinatorial number. Okay. So it increases very badly with the relaxation order and number of variables. So what happens if we want a very tight global optima, then we will need to increase this relaxation order likely, and then this moment matrix will get very large, and we want to avoid this. Okay. So for this, we consider different types of polynomials, so different type of structures that we can exploit. So I'm just gonna put like the easiest example I can think of, which is this polynomial here, and with this we're gonna talk about sparsity. Okay. So for any polynomial that we have, we can define what is called the sparsity graph or the sparsity graph, let's say, which basically assigns a node, a vertex, for each variable that we have. Okay, and then if the two variables appear in the same monomial, like for example this x1 and x2 here, then they will be linked by an edge in this graph. Okay, and we can do this for any polynomial. This one is the simple case. And now once we have built this sparsity graph, what we can do is build some 3D composition of this graph. So we will consider bags of variables such that these bags form a tree. Okay, and now I'll explain why this will be advantageous. So imagine for the problem for this previous example, so in 4 variables, we have this moment matrix, okay, in the SDP for relaxation order 1. So we just have the linear terms here. So this is the moment matrix. And if we increase the relaxation order, then we increase the size of this matrix will increase very fast. Okay, so we don't want this. But what we can do with the structure we just mentioned, this sparsity structure, is that if we have this graph, we can find these bags of variables that define some tree decomposition. And then instead of dealing with checking this matrix to be PSD, what we can do is to check these 3 independent bags here, forming each of them an independent moment matrix. And we can check these 3 moment matrices independently to be positive semi-definite. Okay, so we're gaining, you can see from checking a very big PSD matrix to checking 3 smaller ones. And they will spell better with as we increase the relaxation order. Okay, so a not as easy example. So before the polynomial was really simple, but here, as we can see, similar to before, but here we have like a cycle. So okay, now for simplicity, the 1 is corresponding to x1, but basically this is the correlative sparsity graph of this polynomial. So 1 is connected to 2 and 5, appearing here at the end, etc., etc. And now we want to do the same. We want to build this tree decomposition of these bags of variables. So now we cannot just like do the naive thing we did before, which is connecting 2 and 2, because then it will not form a tree. So what we need to do is find what is called the chordal extension, which basically means adding some chords or some extra edges that will allow us to find the clip tree. Well, these bags are also called clips, and basically this allows us to find this tree decomposition. So now the moment matrix, instead of being the 5 variables, we will have moment matrices of 3 variables, 3, 3, and 3. Okay. Okay. Now let's move to a slightly different topic, and then we'll connect the two. So, as well, the title of the presentation said, what we want to deal with is polynomials that have some type of rank structure. So let's explain a bit how to connect these things. So imagine we have a polynomial, say this polynomial here. So with this polynomial, or for any polynomial, we can build what is called the coefficient tensor, which basically says that, okay, like we take these coefficients and we arrange them in a tensor of this form. For the variable, which is simple, it's a matrix. So we have this coefficient, the 1 here, the 4 belongs to the x2, and then, for example, the x1, x2 squared is this 10 here. Okay, very simple. Now, what happens if this tensor has some structure? So as we can see here, for this example, we can decompose this tensor, this matrix, into this form. So this basically is equivalent to writing the original polynomial, which we just defined, as this form. Okay, so we kind of decouple the x1 and x2, making it a separable polynomial. Okay. Okay, so how does this motivate the no method? So let's consider a further example. Let's take this example here, which is fully dense. So as we've been building the correlative sparsity graphs, this would be the graph corresponding to this polynomial. So as we can see, x1 interacts with all the variables, x2 and x3 and x4 are the same. They interact with all of them. So this will be the correlative sparsity graph. And as we can see, to build these bags, this kind of graph doesn't have any structure we can exploit. Like the best bag we can build is basically with the 4 of them. So the clips or the moment matrix will be basically as big as the original problem. But what happens if we write the polynomial in this coefficient tensor form? So if we do this, we find that the coefficient tensor is basically a tensor with all ones. And basically this means that we can decompose the polynomial in the following form. So this very structured kind of decoupled form. Okay, so we have a fully connected graph here. So that tells us that we cannot exploit any type of sparsity, but we have some kind of algebraic structure here that suggests that maybe there's some structure that we could exploit further. Okay, so our method what tries to do is basically say, how can we make this structure exploitable using moment SOS hierarchies. Okay, so the polynomials we're going to deal with have this general form. You call low rank polynomial if this R is small. So as you can see, these F's here will be univariate polynomials, and then we take a product of them for as many variables as we have. And then we take a product of univariate polynomials, and then we add different components. Are many of them. Okay. So another example. I hope you don't get too tired of 1,000 examples, but here is one more. So we can write this polynomial here as a rank 2 polynomial that we call 2 polynomial. So here x1, x2, x3, x4, x5 are decoupled, and then we have a second sum in the term. Okay, also with decoupled variables. So this would be like a rank 2 polynomial. So the method we call it low rank polynomial optimization, and basically consists of the following. We want to find the infimum of this, so we want to minimize this polynomial. So if we consider this polynomial in its full form, right, we've seen that the correlative sparsity graph is complete. All the variables interact with each other, which means that there's nothing to exploit. But what we suggest is basically to define some new variables, these S's, which are some liftings of this polynomial, that would make the objective function linear in S instead of fully dense in X. So as you see here, we could rewrite this polynomial as just a sum of S variables. And then we would have to add the constraints of these S's, which are defined by some F's. So now I'm going to explain how to define these recursively. But the idea is that basically the first F, so F of X1, will be equal to one variable, is S1. And then the second variable, S2, will be equal to the previous variable, S1, times the current univariate polynomial. With an example, I hope this will become clear. So this is the idea. We have a dense polynomial, it's the same as before. It's rank 2, right? So we have this expression here. And now we transform the infimum of this polynomial, which is fully dense, into the infimum of this, just the sum of two variables, linear, plus these constraints here. So the first term will be 1 plus 2x1, which is equivalent to here. Then the second S will be the first S times this component here, etc., etc. And then we will have we have like different S's for the different rank components. So we define one set of S's for the first one and one set of S's for the second one. So this would be for the second rank component. Okay. So we're going from how many variables? 5 variables to basically 15 variables, but hopefully adding these variables can give us enough structure that is worth this trade. Okay. So how does the graph look now? The correlative sparsity graph of the new problem. So now instead of having a fully connected graph of five variables, now we have a pretty messy looking graph, but I'll commit you that this is hopefully more structured. So remember that these dashed dots are like these dashed lines are the chords that we are adding to break the cycles and build the backs of the tree. So we have this highly structured graph. As you can see, it repeats, like as we increase the number of variables. We add these new lines to build the backs. And then when we build the backs to build the moment matrices, we get something like this. Okay? So originally we have 5 variables here, so a back of 5 variables. And now we'll have many more backs instead of 1, but they will have 4 variables each, as you can see here. Okay? Now the magic of this, well, I put the smallest example that could provide an advantage, but as we increase the number of variables, these backs here will stay of size 4. So we could go to 200 variables, we would have many more backs, but they would still have size 4, which means that the SDP we'd be computing would be just checking the PSDness of many small matrices instead of a very big one, which will be very advantageous for the computation. Okay, so how does it compare, like in size? So for the dense method, we would have a click size, which is equivalent to the number of variables, because all the variables talk to each other and are fully coupled. But with our method, the maximal click size will be the minimum between the number of variables and the rank of the polynomial plus 1. So what does this mean? This means that if we have a very large n, say 1,000, but the polynomial can be written for small rank, say rank 2, like we had now, Then the well, here should be the tree width. Yeah, here might be my +2 actually. Well, but basically this will go from 1,000, which we had previously, to size 4 trees or bats. Okay, so how does this go in numbers? Basically, for the dense moment SOS, we have, for this example, so 10 variables, rank 2 polynomial, and degree 2 univariate polynomials in the univariate factors. Here we have a moment matrix of size 184,000, while for the LRPOP we would have many more packs or clips, but they would have size 15 only. So we would go from something that is totally uncomputable, if it's fully dense, to something that is very manageable for computers. Okay, these are some numerics here. So we randomize the coefficients of the polynomial, and we take some polynomial with rank 2 and degree 2 univariate factors. And we compare the dense method, the dense moment SOS hierarchy, to our LR hierarchy. So here is for 2 different relaxation orders. And this is as we increase the size of the polynomial. Okay, so as we can see here, if we go to, like, the dense method can handle up to n equals 5 variables, but when we go to n equals 6, then it takes a long time, while our method can manage it basically a second and get, I mean, here we're getting type values, so the same values, so we suspect that this value will be the same, also because it coincides the relaxation orders, and we can compute it with basically 0.1 seconds or 1 or 2 seconds. Instead of more than, I think the limit here is 300 seconds. Okay, so how far can we go actually? So for this case, to check the scalability of this, we consider when the univariate factors are formed by Bernstein polynomials. This is a question of conditioning about the polynomials. Because if we consider just random coefficients, if we take products of say 1,000 variables, the coefficients might get so large that the SDP doesn't provide good values. But the point here is that we build some specific type of polynomials for which we know the analytical optimum. So in this case, for rank 2, we know the analytical optimum is 2. And here what we're seeing is that when we solve for this, so this is as we increase the number of variables, we don't get lower bounds, but we get a value that is larger. We suggest that basically the conditioning of the problem is very bad. And even if, I mean, we know that the analytical optimum is 2, but we're getting here for 1,000 variables, 2.73, which is, I mean, quite a large error. But the point here is that it's computationally doable, right? Only 56 seconds we can calculate something like this. Basically, 1,000 variables and degree 2, which means a polynomial of 1,000 variables and total degree of 2,000. So we can compute this with 56 seconds, and it would be like fully dense polynomial. But yeah, what's the big picture of this? So I've been talking about taking a coefficient tensor, and taking like this. It's a CV decomposition, what we're considering, that gives this kind of expression for the low rank polynomial. But I mean, this coefficient tensor is just a tensor, so we can kind of consider any type of decomposition we are asked or we are given, basically. So we could also take, for example, a tensor train here, or a tree, for example. So once we have the coefficient tensor, we can look for any decomposition, or we can expect someone to give us just a decomposed coefficient tensor directly. And the key thing now is that if we can work with this, basically we can also work with this type of decompositions, because if we have these graphs here, given by the tensor networks that I guess all the physicists care about, including myself, by the way, I'm a physicist, so I care about this. So basically, if we have any decomposition, this will correspond to some parallel sparsity graph of the problem. Okay, so we've seen this one here, but basically, if we had a tensor train, we would have a similar parallel sparsity graph, and we could exploit also this structure and get small clicks. We had a tree, we could also exploit this. We just had we have a different structure, and if we had cyclic polynomials, we could in some way also exploit this, although it might be way trickier. We would have to compress kind of different cores here. And yeah, the complexity for this general picture, this is something we're still working on. But basically, the idea is that it would depend on the tree width of the graph given by the tensor network. So if the tensor network is acyclic or is a tree, this would just be 1. So then we'll have the tree width. So this tree width is related to the size of the biggest click or the biggest back that defines the size of the biggest moment matrix. So this will be given basically, it would be system independent, like the size independent of the number of variables, and it would just be given by the number of, by the rank here. So the rank. And if we have a tensor network that has cycles, so this tree width here will increase. So the tree width here will be, for example, for this grid, right? We have many cycles for a grid of size n, then this tree width here, or the size of the backs of the defining the moment matrix, will increase with the system size. Okay, while in the other ones, like in the tensor train, for example, it doesn't increase with the system size. So it's just 2R, this is the one we defined, and then the tree tensor also is independent of the system size. So with this framework, basically, we can say, okay, if you give me either the coefficient tensor and I decompose it into some tensor network for them to exploit this, or if the coefficient tensor is too big and you directly give me some tensor network that defines this polynomial, then we can define some moment SOS hierarchy that exploits this structure efficiently. And okay, just to conclude, so yes, when we have very structured polynomials like the ones we presented, some tensor network polynomials we can call, these can yield new moment SOS hierarchies. So I've explained one of them, but in the line of work with Didi and Milan, we found out like 2 ways of exploiting this structure in very different ways. Then we have, yeah, when we go to very, very large scales, we can have issues, right? As we saw for the birthing polynomials, because basically if we take 1,000 products of a coefficient, then we can go to very large scales, and the SDT solvers might have issues. And yeah, we can generate. So the key of why we can exploit this is basically lies in computation graphs. We also explore this further in the current work we're developing, where we generalize all of this. And then a further thing that would be very interesting, it would be how to mix this approximation with optimization. So what we're assuming is that we're given this tensor network polynomial directly, and then we globally optimize this. But we could also assume that this tensor network polynomial is given from some kind of approximation of a model that someone is giving us. So if this person that would give us this tensor network had some type of error between the model they have and the actual data, we would provide global bounds on the optimization, and then adding this error to this global bound, then we would have global bounds for some data input and some approximate model. And yeah, these are some references to this work. And that's it. Thank you.
Are there any questions? So
Yeah, your last point was very interesting. So let's say that I'm doing like some sort of variational problem with the tensor network, and I see and I know that this is a limited bond dimension, so naturally I have some error, right?
Mhm.
So then you would have a tensor coming from a variational method, which you can decompose because it's structured, right?
Mhm.
And then you can give me like a bound of the error, or what could you?
No, on the error, not like you would have to provide the bound of the error. What I could do is that if this tensor network has some unknown, right, it's a polynomial in some way, then we can minimize this polynomial. So there's 2 layers, right? Like there's the layer of approximation and the layer of optimization. If you do the layer of approximation and you know the error that you have, and then we optimize this and we give you like a lower bound. If we have a lower bound plus the unknown, the error, approximation error, then we have a global bound for the original polynomial.
Obviously, knowing the error is already.
Yes, exactly.
Okay, and then the second question would be, so can you again, because this was a bit quick, going from like the structure,
Yeah,
the general structure of a polynomial to why you would find this natural tensor network tensor.
okay, so I mean, obviously, doing this step here is super challenging, right? Like finding the optimal like decomposition. So in our work, we assume that we're given this structure. So if you just give me this I mean, we assume that we're given this basically, and we're not decomposing the initial coefficient tensor. But the idea is that we just, I mean, the coefficient tensor of the polynomial, it's just a tensor, right? So depending on the polynomial you have, it might have some structure or some other. So for physics, maybe, this is a structure that you would see often, let's say, or for Hamiltonians, you would have some MPO maybe with some variables in each factor of them, and maybe you want to minimize it somehow. I mean, the yeah, like exploring the way of adding non-commutative variables and applying it to physics is yeah, we're trying to see how to do that.
At the beginning, you said that you substitute the PSD condition on the moment matrix with many PSD conditions on the smaller ones. How do they relate? Like, are they equivalent, or is one stronger than the other?
Well, I forgot to mention that, I mean, if you decompose, well, you can either consider this to be PSD or these three to be PSD, but as you can see, there's moments that will coincide, right, in both. So basically, you need to add like some kind of matching conditions also of these moments. But then, yeah, the sparsity graph basically gives you an equivalent moment. So that's fine.
Yes.
In the way. You mean here?
I guess with the dense.
Yes. So using well, we use the TSSOS package. Yeah, but here we see that already we converge into. Well, if we assume that this is the correct optima, then we converge already a realization of it too.
So dense relaxation doesn't keep strong about the general sense sparse relaxation to same order.
But the orders here are different. So the relaxation order for the dense will be given by the total degree of the polynomial and the total number of variables. Well, here is only given by the number of variables in the clique and the degree of the univariate polynomials. It's a bit subtle. Yeah. It's not. They are not equivalent relaxation orders at the dense. We can discuss further.
A product of any things which will hide us. We introduce new variables, so we have quadratic terms.
Well, it's not really quadratic because here we might have univariate polynomials of degree 20, maybe. You know, and here we would have a extra 20. We can discuss further.
We have time for another brief question. If not, let's thanks again, Llorenc.